Smart bombs changed the meaning of air warfare forever. Before their arrival, bombing was largely an exercise in probability. Aircraft flew high or low, released unguided bombs, and hoped gravity and numbers would do the job. Accuracy depended on pilot skill, weather, altitude, and luck. Entire formations were required to destroy a single target, and collateral damage was often unavoidable. Smart bombs emerged to solve this problem by adding guidance, intelligence, and precision to a simple concept: a bomb that knows where it is going and adjusts its path in flight to hit exactly what it is meant to hit. At their core, smart bombs are air-dropped weapons equipped with guidance systems that steer them toward a specific target. Unlike traditional, dumb bombs, which follow a purely ballistic path, smart bombs can correct their trajectory after release. This ability transforms a free-fall munition into a precision strike weapon. The result is fewer aircraft required per mission, fewer bombs needed per target, and a significantly higher probability of success, even against hardened or well-defended objectives. The idea of guided bombs is not new. Early experiments date back to World War II, when engineers tried to guide bombs using radio control or simple visual tracking. These early systems were crude and vulnerable to interference, but they proved a crucial concept: guidance could turn airpower into a scalpel instead of a hammer. The real breakthrough came decades later, when advances in electronics, sensors, and computing made reliable guidance practical on the battlefield. One of the most well-known types of smart bombs uses laser guidance. In this system, a target is illuminated by a laser designator, which may be carried by the attacking aircraft, another aircraft, a drone, or even troops on the ground. The bomb's seeker detects the reflected laser energy and steers toward it. As long as the laser remains on the target, the bomb will track it with remarkable accuracy. This method allows precision strikes against moving or time-sensitive targets, such as vehicles or fortified positions. Laser-guided bombs gained global attention during conflicts where precision strikes were televised and analyzed in detail. Viewers saw bombs entering windows or destroying bridges with a single hit. However, laser guidance has limitations. Weather conditions such as clouds, smoke, or dust can scatter the laser beam, reducing accuracy. The laser must also remain fixed on the target until impact, which can expose the designator to enemy fire. To overcome these limitations, satellite-guided bombs were developed. These weapons rely on global navigation satellite systems, such as GPS, to determine their position and guide themselves to pre-programmed coordinates. Before release, the target's coordinates are entered into the bomb's guidance unit. After release, the bomb continuously compares its current position to the target location and adjusts its flight path accordingly. This allows accurate strikes in all weather conditions, day or night, without the need for continuous target illumination. Satellite-guided bombs revolutionized modern air campaigns. They allowed aircraft to operate at higher altitudes, reducing exposure to air defenses, while still delivering precise effects on the ground. They also enabled rapid targeting of fixed infrastructure such as command centers, bunkers, airfields, and supply depots. However, satellite guidance is not without challenges. It depends on access to navigation signals, which can be jammed or degraded in contested environments. Another important category combines multiple guidance methods into a single weapon. These dual-mode or multi-mode smart bombs can switch between guidance systems depending on conditions. For example, a bomb might use GPS guidance to reach the general area of the target, then switch to laser guidance for final precision. This redundancy increases reliability and flexibility, ensuring the weapon remains effective even if one guidance method is disrupted. Smart bombs are not just about guidance, they are also about integration. Modern air forces integrate these weapons into complex networks involving sensors, intelligence platforms, and command systems. Satellites, reconnaissance aircraft, drones, and ground observers all contribute data that helps identify and verify targets. This information is processed rapidly, allowing decision-makers to authorize strikes with greater confidence and speed than ever before. The impact of smart bombs on military strategy is profound. Precision reduces the need for mass bombing campaigns, which in turn lowers logistical demands and operational risks. A single aircraft armed with smart bombs can achieve what once required an entire squadron. This efficiency allows air forces to project power more effectively while minimizing losses. It also changes how conflicts are planned, shifting emphasis toward intelligence, surveillance, and target validation. From a tactical perspective, smart bombs give commanders greater options. They can strike high-value targets deep inside defended territory without launching large-scale assaults. This capability can disrupt enemy leadership, communications, and logistics early in a conflict, potentially shaping the outcome before ground forces are heavily engaged. Precision also supports close air support missions, where friendly forces are operating near enemy positions and accuracy is critical. There is also a humanitarian dimension to smart bombs. By increasing accuracy, they can reduce unintended damage to civilian infrastructure and non-combatants when used correctly and with proper rules of engagement. Precision does not automatically guarantee zero collateral damage, but it provides the tools to minimize it. This has become increasingly important in modern conflicts, where military operations often take place in or near populated areas. Despite their advantages, smart bombs are not a magic solution. They rely on accurate intelligence, correct targeting data, and disciplined decision-making. Errors in any of these areas can lead to unintended consequences, regardless of how precise the weapon itself may be. Moreover, adversaries adapt. Camouflage, decoys, hardened shelters, and electronic warfare are all used to reduce the effectiveness of precision-guided munitions. Cost is another factor. Smart bombs are significantly more expensive than unguided bombs. While they may reduce the number of weapons needed per target, their higher unit cost can strain defense budgets, especially during prolonged operations. As a result, many air forces maintain a mix of smart and conventional munitions, selecting the appropriate weapon based on mission requirements. Technological evolution continues to push smart bombs forward. Newer designs feature improved seekers, better resistance to jamming, and enhanced accuracy. Some incorporate data links that allow in-flight retargeting, enabling pilots or commanders to change the target after release if the situation on the ground changes. Others are designed with reduced radar signatures or specialized warheads for specific targets, such as hardened bunkers or reinforced structures. Artificial intelligence and machine learning are also beginning to influence the future of smart bombs. Advanced algorithms can improve target recognition, guidance efficiency, and decision support. While fully autonomous weapons remain a subject of intense debate, incremental advances in automation are already enhancing performance and reliability. Smart bombs have reshaped how the world views air power. They symbolize the shift from brute force to precision, from mass to accuracy. Their presence influences diplomatic calculations, deterrence strategies, and military planning. The knowledge that critical assets can be struck accurately from long distances affects how nations build defenses and structure their forces. In the end, smart bombs are more than just weapons, they are a reflection of how technology, strategy, and ethics intersect in modern warfare. They demonstrate how innovation can change not only how wars are fought, but how they are perceived. As technology continues to advance, the role of smart bombs will likely expand, becoming even more integrated into the complex systems that define 21st-century military operations. Understanding smart bombs means understanding modern conflict itself. A battlefield where information is as important as firepower, precision rivals sheer strength, and decisions made far from the target can have immediate and decisive effects. This is why smart bombs remain one of the most influential developments in the history of military aviation, and why they continue to shape the future of warfare.